Okay, let's continue. So now let's consider another example about fair allocation. Suppose that we have $1,000 and we want to allocate this $1,000 to two persons in a fair way. Okay, the fairness may need some definitions. Here, let's use the easiest one. Is that we want to minimize the smaller we want to minimize the difference between the two amounts. Okay, so for example, in the best way of doing this allocation, we would give each of them 500. In that case, there is no difference between their part, and then we say this is the fairest way of doing the allocation. If we do 400 and 600, then it's $200 of difference. It's not as good as 500, 500. So for this problem, it's so simple. We don't need any formulation to do this, do that. Okay, but in general, you may have a more complicated problem. For example, you may have multiple resources to allocate. Okay, you have cash, you have some derivatives, or you have some houses. Okay, you have some goods to allocate to multiple entities or persons. Okay, and for different items, there may be a different way of measuring fairness. So let's still focus on this very basic problem to see how may we formulate a linear program, okay, a linear program to achieve fairness in this allocation problem. Okay, $1,000 allocated to two persons, and we want to minimize the difference between the two parts. Suppose we say xi is the amount allocated to person I from 1 to 2. Then let's consider this formulation. Okay, I know each of them must be non-negative. The sum of them must be 1,000. And I want to minimize, well, their difference. So x2 minus x1. Is this correct or wrong? Well, unfortunately, this is wrong because if x2 is greater than x1, then this is okay. x2 minus x1 is the difference. But if x1 is greater than x2, this difference is going to give you a negative number. However, in that case, what we really want is, in some sense, the absolute value of that difference, right? So this formulation is not really correct. If we really solve this problem, the optimal solution would be to give x1 the everything and to give x2 0. In this case, your objective value is negative 1,000, which is the smallest, but it's not what we want. So the right way of doing the formulation is to add this absolute value function to x2 minus x1. Okay, then this is really what we want. Unfortunately, even though this is a correct formulation, this is nonlinear. Okay, because the absolute value function is nonlinear. Graphically, we can say, suppose I want to draw, for example, absolute value of x. I know it would look like this when x is positive, or this when x is negative. It's obviously not a linear function. Okay, a linear function must be a line, a line, a line, a line, a line. It cannot be two lines combined together. So an absolute value function is nonlinear. So we want to ask whether there is any way to make this a linear program. Indeed, there is one, and we're going to tell you how. So first, let's use another variable to denote the absolute difference. Okay, I'm going to use w to replace the absolute value of their difference. Okay, so from the original formulation to here, nothing is different. And then I still want to deal with this absolute value function. I look at this constraint and I realize that I can change the equality to an inequality. Why? If you look at this inequality again, we can tell you that any optimal solution, at any optimal solution, this constraint is binding. Okay, this constraint is binding. If this constraint is not binding, that means we can decrease W a little bit to still satisfy all the constraints, but improve our objective value a little bit. Okay, so that means this constraint must be binding at any optimal solution. If that's the case, we can say these two programs are equivalent, because even though this is giving you a larger feasible region, eventually what really matters is the feasible region specified here. So these two these two programs are the same or are equivalent. Now, we know that an absolute value function is nothing but a maximum between its value and its negation. Okay, to really see it, you may want to draw a graph like this. Suppose I want to talk about x and x bar, and then this is x. This is negative x. And whenever I want to compare x and negative x, I pick the maximum part. That's my x bar, absolute value of x. So even though here I'm having a function of two variables, it's still the same thing. I am asking whether this is positive, or if this is actually negative, then I want to choose the negation of it. Okay, so an absolute value function is just a maximum function. So what I'm talking about is for W to be no less than a maximum of two things. In this case, I do an observation and say that, oh, actually I just need this. Okay, this and that are identical. Why? Suppose W is greater than the maximum of two numbers, then W would be greater than each of them. Correct. Or in the opposite way, if W is greater than this and that, then W would be greater than the maximum of both of them. Fine, right? So these two things are just equivalent. But now, the intersection of these two, okay, is linear, while this one is not. So we can linearize this nonlinear constraint into two linear constraints. Okay, then we're done. The linear program we want is actually this one. I want to minimize something called W. W is the absolute difference. And then all I need to do is to say that W is at least x2 minus x1, or W is at least x1 minus x2. One of these two terms, only one of these two terms can be positive, and W would be equal to that amount, that positive amount. I mean non-negative amount. Okay, so basically that's right. But if we really want to verify this, okay, we can solve this LP to see if we can really get 500. Or we may replace this number to any positive number k, and then we want to know whether we always get k half. Okay, so that can be done. For example, you have the simplex method, right? You simply apply your simplex method to solve this problem. You will get 500. Here, let's use another way to do the verification, okay, which is easier with just pen and paper. Okay, for this LP, I understand that this equality constraint actually allows us to remove one variable. In any case, x2 is just 100 minus x1, right? So why don't I replace this 2x2 to 100 minus x1? In that case, I don't need the first constraint anymore. The second constraint would become w greater than or equal to 1000 minus x1 minus x1. So it's this one. Or the next constraint, w is greater than or equal to 2x1 minus 1000. And now I only have x1, so x1 must be non-negative. Graphically, you can solve this linear program, right? Maybe something like this. I now have x1 and w. The first constraint says that when the x1 is 500, w is 0, or when x1 is 0, w is 1000. Okay, so it's here. The other constraint is that when x1 is 0, w should be negative 1000. So maybe here. Okay, now in either case, I am saying that w must be at least that amount. So your w would be here. Okay, this is your feasible region. And don't forget that x1 must be non-negative. Now, what we want is to minimize w. Okay, minimize w. So the optimal solution must be here. And it's very easy to verify that this is indeed 500. Okay, so this very quickly verifies that our LP here really gives you the fairness allocate, the fair fair allocation. Okay, a fair allocation 500. The key point here is that we linearize a absolute value function to two linear constraints. In the next video, I'm going to tell you in general how may we do that for more similar situations. Thank you.